Okay, in this lesson we're going to graph a rational function. A rational function is defined to be a polynomial divided by a polynomial. This is one of my favorites to graph. You'll see why when we're done. So let's go through the steps, and hopefully these will start becoming kind of used to them. Domain, x can't be 0. So let's just write it like that. Intercepts. Well, since x can't be 0, there's no y-intercept. And the x-intercept would be where y is equal to 0, where the value of the function is 0, which would be when x is equal to 1. So 1, 0 is the x-intercept. Okay. What's next? Oh, and then after that, let's make our little line and number line and put in these values, 0 and 1. Those are the places where the function might change from positive to negative. And so if you put in something larger than 1, everything is going to be positive. Put in a half, you're going to be negative. Put in -1, and you're going to be negative on top and positive on the bottom, so also negative. So there's your function. Okay, then what? What's next? Let's see. Symmetries. And so let's do it over here. If you put in f of -x, you're going to get -x minus 1 all over -x quantity squared, which will be just -x minus 1 over x squared. So notice that you don't have the original function, but neither do you have the opposite of the original function. If you factored a negative out of the top, you'd be left with a x plus 1 there. So it's neither even nor odd, so there's no symmetries. There you go. Then what? Asymptotes. Well, okay, so we have now a place where the denominator goes to 0. So that will more than likely lead to a vertical asymptote. Let's see if it does. So we'll look at the limit of this function as x goes to 0. And here's the way I like to do it. I just kind of put the numbers in my head, and I say, well, as x approaches 0, this numerator is going to approach -1. And the bottom is going to approach 0, but this is very important. The bottom will always be, the denominator will always be a positive number. See that? Because you're always squaring this thing. And so the top will be close to 1, the bottom will be going to 0, so the ratio is going to be going off to infinity, and in this case it's going to be -infinity. If this were just an x on the bottom, then as you come in from the left and as you come in from the right, you're going to get one going to plus infinity and one going to minus infinity. So, it might look like this. One goes up, one goes down. But in this case, notice that with the x squared, they both go down. Okay? So there you go. So asymptote, I guess we'll just write this here, that the x-axis, or we can just say x equals 0 is a vertical asymptote. Let's just write it this way: vertical, x equals 0. And let's be more specific. Let's actually write this limit in there. Limit of f of x as x approaches 0 is equal to -infinity. Okay, so that's all the information we need. And now let's see what happens as x goes to infinity. Well, now remember the rule. You have a higher power of x on the bottom than you do at the top, so this is going to get big faster than this, so the limit's going to go to 0. The way to prove that, recall, if you want to go through the steps, is to multiply both the top and the bottom by, in this case, the highest power of x on the bottom, which is going to be 1 over x squared, And so that's going to be what? 1 over x minus 1 over x squared, all divided by 1. As x goes to infinity, that goes to 0, that goes to 0. 0 over 1 is 0. So and it doesn't matter whether it goes to positive infinity or minus infinity, these are going to go to 0 either way. So let's just write that down. The limit of f of x as x goes to infinity or minus infinity, they're both equal to 0. And so y equals 0 is a horizontal asymptote. Horizontal. Okay, see what we can do with limited board space here. So now we get into the more fun part. This is all the stuff, again, that doesn't require calculus. Now we want to know where it's increasing or decreasing. So we take the derivative, and here we go. Take the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Bottom squared. So if you take x squared and square it, you're going to get x to the 4th. And so let's go ahead and simplify so we can figure out where this thing will be equal to 0. Here you're going to get x squared. Here you're going to get minus 2x squared. And then here you're going to get plus 2x all over x to the 4th. And then you can combine these. This will be, let's write it as 2x minus x squared. See that? 2x minus x squared. And then we can factor an x out. And we'll be left with x over 2 minus x on top and x to the 4th on the bottom. And then I can cancel one of the x's and be left with 2 minus x over x cubed. So there it is. And now with that, we can hold on just a second. Plug in the computer. And now with that, we can check to see where this thing is positive and negative. And so we'll put in 0 here and a 2 right there. And when x is bigger than 2, we're going to have negative on top and positive on the bottom, so the whole thing will be negative. If you put in a 1 here, it's going to be positive on top, positive on the bottom. And if you put in a negative 1, 2 minus a negative 1 is going to be positive. And negative 1 cubed is negative, so it's going to be back to negative again. Which again, you should be able to see because this is an odd power and that's also an odd power, so it should change for each of those. So this is your derivative. Again, be careful. That means that the function is decreasing here, increasing here, and decreasing there again. Okay? Now let's go ahead and take the second derivative up here. So this is going to be for concavity. So f double prime of x is equal to, we'll use this right here. Notice why it's so important to simplify. You'd hate to take the derivative of this thing. Much easier here. Take the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So you get that. Again, go through the same simplification, just the right amount of algebra in this problem. That's why I like it. And so here you're going to get minus x cubed. Here you're going to get minus 6x squared. And then here you're going to get plus 3x cubed all over x to the 6th. Now what? 3x cubed minus x cubed is going to be 2x cubed. And then minus 6x squared. You can factor let's factor 2x squared out. And if you do, you're going to be left with x minus 3. And x to the 6th down here. And then 2 of those x's cancel out, and you're left with 2 times x minus 3 over x to the 4th. So we'll do the same thing. Say, when will this be 0 or undefined? Either at 3 or at 0. And we'll check all sides. If you stick in a 17, you're going to get positive, positive. Stick in a 2, you're going to get negative, positive. And stick in a negative 5, you're going to get negative, positive again. So this is f double prime. I always like to mark them just so that you keep track of which is which. Second derivative, if it's negative, that means it's concave down, and concave up. So let's see what it looks like. Plenty of room here. So let's see. I always like to put the important points on first. First of all, notice that 1, 0 is a intercept, and at 2, the derivative changes. It goes from positive to negative. So let's find the value at 2. 2 minus 1 is 1 over 2 squared is 1/4. So let's say that that's up here, just to make it a little bit easier to see. So there's 2 1/4. And where else? Oh, and I also like to do this. It's increasing until you get to 2, and then decreasing after you pass 2. So it's a little relative maximum right there. So I just like to put as much stuff on as you can fit on the graph. At 3, what happens at 3? First of all, it's going to be an inflection point because the concavity changes from negative to positive there. What's the value at 3? It's going to be 2 over 9. So down just a little bit from here. Let's put it right there. So 3 2/9. And that should do it. Let's see once what happens. So over here, what's happening? The function is decreasing. It's has, oh, I also like to do this. It's got an asymptote along the x-axis, which is y equals 0. It's also got an asymptote right there. So I put little dots there just to remind me those are asymptotes. So this is an asymptote, this is an asymptote. It's decreasing and it's concave down. So that doesn't give you much choice. It's going to look like that. Once you pass 0, then what happens? It's increasing. It's concave down all the way until I get to 3. So it's increasing. It goes through this point. It increases until it gets to 2. So it must look something like this. Increase until it gets to 2. Once you pass 2, it starts decreasing. It's still concave down, so it's still below the tangent line. Once you pass 3, it becomes concave up. And it's still decreasing all the way. It just becomes concave up. So it looks something like that. So there you go. Not bad. Not a bad looking graph, if I do say so myself. And so there it is. That I can show you now why I like it. Because the algebra is just about right. It checks to see whether you know how to do the standard algebra. And you have to do the algebra in order to get the answer. And all the kind of important things happen at nice numbers. 0, 1, 2, and 3 is where all the stuff happens. And so there you go. So there's a rational function for you. Okay, very good.